the fact that we write down all languages, L1, L2, L3, and that would mean that every language that we can conceive must be in this enumeration. Enumeration of all languages. And now, let me define a new language. And what I'm going to do is I'm going to look at this language and I basically define it in the following way. This is the set of all VIs such that VI is not in LI. So in other words, I am looking at the diagonal here. So this is this, which this is of course a 0 or a 1 because these are our bit vectors here. So this is a 0 or a 1. This is a 0 or a 1. This is a 0 of a 1. So I'm going to go down this diagonal. This is obviously an infinite diagonal. And so basically what I'm doing here is I'm flipping each of these bits, because essentially I'm saying that that new language that I'm creating consists of all those VIs that are not in LI. So I'm saying if there is a 0 here, then I am putting a 1. If there's a 1, then obviously I'm putting a 0. So I'm flipping every single one of these bits in the diagonal that basically says V1.
You're muted.
Thank you. V1 is in L1 or not, and if it is, then it is not in L, and if V1 is not in L1, then it is in L. And the same thing for V2. So basically we're flipping all the bits in the diagonal. And now, this is of course a language, because I defined a bit string that indicates for every one of those words whether or not it is in that language. And now comes the important observation. If this is indeed an enumeration of all languages, then L must occur. Right? That L is a language, and if this, which is what we are assuming, is an enumeration of all languages, then this L must occur. So let's assume that there exists a J such that Lj is L. That's what that would imply. And that, of course, immediately gives a contradiction, because let's look at Vj. Vj, by definition, is or is not, depending what happens, may or may not be in Lj. If it is in Lj, then it is not in L. If it is not in Lj, it is in L by definition, because basically we flipped every bit in that diagonal, and therefore this is a contradiction. And it is a contradiction to what assumption? Well, we made only one assumption, and that is that this is an enumeration. So no, the languages are not infinitely enumerate. There are significantly more than just countably many. So that means that the whole argument that this, by assumption, is an enumeration is, of course, wrong. We cannot enumerate, and that means that, can you hear me?
Yes.
Yes, okay. Something weird went on. So that means that this is on whoever keeps on muting me. So that means that this is not possible. We can't enumerate all languages. And so what does that imply? That basically implies that you have a set that is far larger than countably infinite. If you know about the cardinality of the real numbers compared with the cardinality of the rational numbers, well, the rational numbers are countably infinite. The real numbers are not. And so the languages that we've defined, set of all languages that we have, is of the same cardinality as the real numbers. Now, what are the implications of that? The implications of that are that if you look at the description of a language, then obviously that is a description, that is a finite string over a particular alphabet. So this whole idea of words that clearly are enumerable applies also to descriptions. Any description is a finite string of over a particular alphabet, and that means that every description of a language is a finite string over a specific alphabet, and that means that all the languages that can be described are only countably infinite. So what that really in practical terms means, that if you look at the set of all languages, then you have essentially for every language that be described, every language that can be indicated in some fashion, for every one of those languages, there are infinitely many languages that you are not going to be able to describe. So that is an important issue here, because it shows you that there are many languages, infinitely many more languages that cannot be described than languages that can be described, because every description, however you do it, is necessarily a finite string of an alphabet, and the result is that there are many, many languages that simply cannot be described. And that is immaterial of whatever way of describing a language you use. which brings us now to the first type of device, finite atomic.
Professor, I have a question before we go to this next part.
Yes, go ahead.
So, could you give us an example of what you're talking about? Like, I understand the mathematics and the discrete math that's going on in here. I can see that you can make it incountable, but why? I mean, how does that actually work in like you said, a practical example?
Well, there is obviously no way I can give you a language that can't be described, because that in and by itself would be a contradiction in itself.
But there are languages that can be described, and those.
Yes, of course, and we will spend all of our time with those languages that can be described, because I am not going to give you an infinite description, because I would never finish.
Makes sense. All right, I understand.
I mean, my usual joke is we research. Okay, so the issue here is that it is important to understand that there are basically infinite, for every language that you can describe, there are infinitely many languages that cannot be described, and that is independent of how clever you are, because essentially any description is a word over a particular alphabet, and that immediately implies that all those descriptions are enumerable, since there are many, many more languages that are not countably many, because that would be the contradiction that you can't enumerate languages. It follows that you have many, many more languages that cannot be described. This doesn't really have any practical implications other than that, obviously, if you take a set of languages that you can describe, then you have no complement of the set of languages is, of course, not countably infinite. It is uncountable. It is obviously infinite, but it's not countable. Okay, any other questions? All right, then let's look at finite automata.
So
Yes.
one student asked because they were having trouble with their audio. They were asking what like the gist was of what you had just been speaking about, so that they can go back and like Google that and study what you were just talking about.
You're talking about this?
Right.
Well, basically, I have shown that given the fact that all words over a specific alphabet are enumerable, we've established that, we then wanted to ask whether one can enumerate all languages. Obviously, there are infinitely many languages, but are they enumerable? And the answer is no, and the way you show that is by constructing a language, which basically is formed by taking as a bit string that defines it, the flipping each bit on the diagonal, and then that defines obviously a language. If this were an enumeration of all languages, then that language would have to be there, and we then obviously can show that that language cannot be there, because if it were a particular language, it would have an index j, so that language L would then be equal to Lj, and then we simply consider the word Vj. If it is in L, it cannot be in LJ by definition, and if it is in LJ, it cannot be in L, and therefore that gives a contradiction. So this language cannot be part of that enumeration, which means it isn't enumeration.
Thank you.
Okay. So let's look at the first, in some sense, the simplest way of defining a language that can be described, and that is using a finite automaton. So let's look at a simple example. I will draw a graph, and I will explain in a minute what the significance of the various components of that graph are. B, A, B. So now we have, what do we have? We have basically a graph that consists of 4 nodes, and there are edges between the nodes. So this is a little bit more than a typical directed graph, because what we have here are edges, edges that are labeled with letters from an alphabet. In this case, we are assuming that the alphabet is A and B, little a, little b. And then we have these nodes, which are called states. So we have states. We have double circles. These are final states. We'll get to what that means in a minute. We have a single state that has an arrow going into it. It is called the initial state. And then we have edges, labeled edges from a state to another state with a label. So this is called a transition. Well, in this case, it's a B. So what we have in this case is, of course, a transition from one state to another state. Now, remember, we are in the business of defining a language, and that means we have to describe how that finite automaton can be used to define a language. And so if you recall, when we talked about automata, they basically are black boxes where we feed in a word and the black box tells us yay or nay. Yay, yes, the word is in the language, and no, it isn't. Now, of course, this is no longer a black box. We can actually look at this, how it works. And that means we now have to see how we use these states and those transitions. Now, the initial state, of course, obviously suggests that that's where we start our game. So if we have, so let me call this Q0, and this is Q1, and this is Q2, and this is Q3. Then if I look at a word, say I start with A, and I start in state Q0, well, if I consider what happens from state Q0 under the letter A, well, there is a transition with that A, which gets us back to Q0. Okay? And then if I have a B, then that gets me from Q0, where I am currently, to Q1. And if I have another B, then I have Q1, Q2. And if this is the entire word, then I end up in Q2. And since Q2 is a final state, that word is accepted. It means the word is accepted. It is a word in the language that is being used by to define the language. Okay, so if you, let's take another word. Let's take B. So we always start in the initial state. There is only one, so there's no ambiguity. And then we have a B that gets us to Q1, and then we have another B that gets us to Q2, another B gets us to Q3, another B that gets us to Q0. And if this is the word, then B, 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 B is rejected, because Q0, where we ended up, is not a final state. Okay, so does everybody understand how we play this game? All right, now the question is, can we actually describe in ordinary English what this language accepts? All the words, the entire language. In this case, it is not very hard. That's why I use it. In general, it's quite a bit more complicated to come up with a description of a particular language that is involved in that kind of thing. But if you look at this graph, what do you see? Well, first of all, you can obviously observe that wherever you are, the A is not going to get you into a different state. So if you have a letter A, it doesn't change anything. So for all practical purposes, wherever we are, we stay with A if I have a letter A. So we can, in fact, ignore the letter A completely for all practical purposes. And that means in this particular example, that's of course not true in general, but in this particular example, the only thing that is of relevance is what happens with the letters B. And now, if we look at what happens with the letter B, well, we start in Q0. And what was that question? A, well, A is a letter of the alphabet, little a, and little b is a letter of the alphabet. And now what we're doing is we play this game given a word. So if I give you A, B, B, A, B, B, A, B, we want to know, is that word accepted? So we go A, B, B, A, B, B, A, B, which means we end up in Q1. Q1 is not a final state, so this means this word is not accepted. Okay, whoever wrote that last thing before it disappeared, say it.
I'm not sure what they asked, but I have a question. So whether a word is accepted or not by an automaton is dependent on whether it takes the state from the start state to an acceptable finish state?
the final state or not. If it gets you to a final state, then the word is accepted. If the word doesn't get you from the initial state to a final state, then the word is rejected. Okay? So, that means, can anybody give me a description of all the words that would be accepted by this automaton?
Could you repeat the question?
Can anybody give me a description in English that describes all the words that are accepted, that basically go from the state Q0 to one of those two?
It has to end in either B or BA.
Isn't it? Is uncountably infinite?
No. First of all, the words are all countably infinite. And yes, this automaton will accept infinitely many words, but that's not really a description, that is a characteristic. Well, first of all, these are accepted, not acceptable. Accepted words, and accepted words would have to end up either here or there. So since we have already said we can dismiss anything that the A does, the only thing we have to count is the number of B's. So obviously if we have 2 B's, we get to Q2. If we have 3 B's, we get to Q3. And then we can go around again. So the number of B's, which is has to be a number that is either 2 or 3 modulo 4.
Could you explain what you meant by that? The 2 modulo 4 part?
If you look at this automaton, the automaton basically is a cycle of length 4. Okay?
Okay.
Under B. As I said, we're ignoring the DAs because DAs are not really relevant. So if we look at the B's, if you have a word, strip out all the A's, so that means this word has 1, 2, 3, 4, 5 B's, and so where does it end? 1 B, 2 B's, 3 B's, 4 B's, 5 B's. It ends in Q1, and Q1 is not a final state, and therefore that word is not accepted. So a word has to end up in Q2, or it has to end up in Q3, and that means we need 2 plus any multiple of 4 B's, or we need 3 plus any multiple of 4 B's to end up in these two, in either of the 2 final states. So the W is in 0, 1, in A, B star. The number of B's in W is 2 mod 4 or 3 mod 4. That would be a description of all the words that are accepted by this automaton. what, well, you need to know what modulo 4 means. This is basically the number. 2 mod 4 is 2 plus any multiple of 4. 3 mod 4 is any multiple of 3 plus any multiple of 4. Okay? So, everybody clear that this is what this automaton does?
Could you read off the sentence one more time with the description? Where it says B, I'm sorry, W.
In A star, this is of course A, B star, so it is a word consisting of A's and B's, and the number of B's in W is 2 mod 4 or 3 mod 4. So now we have to be a little bit more formal, and we have to define formally what a finite automaton is. So it turns out that what this automaton is, it is a deterministic finite automaton. Why is it deterministic? Because if I'm in any state in this automaton, and I have a letter, there is exactly one transition. So the easiest way to see that is by simply writing down all the transitions. We have Q0, we have Q1, we have Q2, and we have Q3. And we have 2 letters, we have A and we have B. From Q0 under A, I go to Q0. From Q0 under B, I go to Q1. From Q1 under A, I go to Q1. From Q1 under B, I go to Q2. From Q2 under A, I go to Q2. From Q2 under B, I go to Q3. From Q3, under A, I go to Q3. From Q3 under B, I go to Q0. Now, when I say that given any state and any letter, there is exactly one transition, that basically means that in each entry here, I have exactly one state.
I'm sorry, when you say each entry here, what are you gesturing towards? I don't see your mouse.
In each entry in this table here, I have Q0 under a letter. In each, there are 2 entries, one for A and one for B. Q1, 2 letters, 2 entries. Q2, 2 entries, 2 letters, and so on. Each of those entries has to contain exactly one state. If that is the case, then the automaton is called a deterministic finite automaton. All right, so now we have to define slightly more formally what we mean. We have D with a wiggle underneath. This is an alphabet, a set of states, a transition function, an initial state, and a set of final states. So A is alphabet of input symbols. Q is a finite set of states. It's non-empty, but that becomes obvious. Tau is the transition function. And tau is basically a function that takes a letter and an alphabet and gives us back a letter. So it maps pairs of state and letter into states, which of course is exactly what this does. You're given a state, say Q1, and a letter, say B, and that will give you another state, Q2. And then you have Q0 has to be an element of capital Q. That's why I didn't really have to write down that capital Q has to be non-empty, because we stipulate that Q0 at a minimum is in capital Q. This is called the initial state. Yeah, man. No, I don't want to paste this nonsense.
Try the delete key or the Control Z.
Control T.
Control Z.
Control Z. No, doesn't do anything.
In the top left, next to the save icon, there's a little like a reverse arrow, like a horseshoe kind of looking arrow. That might be the undo button.
Well, I don't have that.
I can see it on your screen. It's at the top left.
Oh, up here.
Yeah. Next to the little the floppy disk icon, up to the left.
Left.
Up.
In the orange portion?
Yeah.
Right.
There you go. I think that's that right there. I think that's undo. There we go.
Thank you. Okay. All kinds of things. So Q0 is the initial state. It is an element of the set of states. It's a single initial state. Some textbooks allow you to have more than one in some contexts, but we don't. And then finally, F is a subset of Q. It is the set of final states. Now, at this point, the only thing that is probably somewhat non-obvious, but it should be fairly clear, is the transition table. The transition function is, of course, this kind of thing here. And so it basically takes a state and a letter and gives back another state.
Is this transition table essentially what the automaton is?
There are a few things missing. What is missing? There is missing which of those four states is the initial state. So if you indicate that, then you can remedy that. And then there is missing an indication what are final states. And so if we add another column where we indicate for each state whether it's accepting or rejecting, then we actually have that. So Q0 is rejecting, so we're going to write a 0. Q1 is rejecting, so we'll write a 0 in that final column. Q2 is accepting, therefore we put a 1. And Q3 is also accepting, so we put a 1. And if you take now this augmented transition table, then in fact it gives you everything that you want to know about the automaton. Because now the alphabet is, of course, up here. This is A and B. The set of states, Q, is, of course, listed in that first column, Q0, Q3 in this case. The transition function is that function before we added things. and then Q0 is the initial state. We needed that arrow to one of them. In this case, it is Q0. And we had to indicate what are the final states. And we did that in the last column by indicating that Q2 and Q3 are final states, and Q0 and Q1 are not. And so with that enhancement, with those two additions, what is the initial state and what are the final states, this actually is a complete description of what we have formally written down here: alphabet, set of states, transition function, initial state, and set of final states. So with that addition, yes, you are absolutely right. This enhanced transition table, which is usually referred to as the state transition table, will actually give you everything that you need to know about this automaton. Okay? All right, so now we have to do one more thing. We have defined what is the automaton, but we still have to define what is a language, the language accepted by the deterministic finite automaton. Well, in order to be able to do that, we have to actually do some additional work. This is what we're obviously interested in. But in order to be able to define that, we have to extend tau to words. At this point, if you look at your transition table, which you have here, it basically tells you what happens from a state under a single letter. So that is where you have this mapping, a state and a letter. Tau of Q and A is going to be some state P. But what we really want is, we don't want to know tau just for letters. We want to extend it to words. Tau, we want to go from Q cross A star. And in this particular case, it turns out that this still gets us to single states. So in that case, what we want to do is we want to do tau of Q and W, which is going to give us some state P. So these are states, and then there, instead of a letter, which we would have here, we want a word. And so we have to extend that transition function, tau, to words. Now, I'm somewhat cheating here. If you're very mathematically oriented, you will probably take offense, because I'm going to use tau for the extension as well. If you want to do some fancy mathematical stuff, you would have to denote that we're now talking about an extension of tau, which may be tau hat or tau star or whatever. I'm going to suppress that because it is fairly obvious what we're doing. But mathematically, I'm being somewhat abusive here.
So is it fair to say tau describes the transition states for not only valid words, but also invalid words? Because it's all combinations of letters in the alphabet?
You don't know whether the word is accepted or not until you're done.
Okay.
So if you look at BBB, that would be an accepted word, but if you now have another B, then it is not. So necessarily you would have to be able to first determine where do you end up, and then you're going to ask, is this a final state? Only at that point will you know whether the word is accepted or not. Okay?
So if there had not been, so like you have an A for each of those states, but let's say on that third node, Q3, you didn't have a transition state for the input of small a,
Yes.
and then you had...
It would not be deterministic.
Okay, okay. So deterministic means that if for each state, it has a transition for every letter.
Because in
Okay,
that
thank you.
case, what would happen is that for Q3 here, you would not have anything under A. And that would not be acceptable.
Thanks.
So that would render it not deterministic. Now, we will eventually talk about an extension of deterministic finite automata to non-deterministic finite automata. At that point, then, we will permit these types of things, but at this point, we don't.
Will we put any value judgment on if something is a deterministic finite automaton? So like
we'll get to that. You don't really know at this point what is a non-deterministic finite automaton, so let's not get sidetracked by that. But also, we don't have any value judgments. We only talk about mechanistic types of things, and non-deterministic automata, once we've defined them, will be much more complicated in some sense. But let's not get ahead of ourselves. All right? So what we have to do is now we have to extend our transition function, which is defined initially just for states and letters, to states and words. And so all this is done using the usual inductive method. So we're going to do, this is our basis, tau of q and epsilon. Basically, this is inductively defined according to the length of the word. We have this word W that we're interested in, and obviously the shortest word is epsilon. And so what would you suggest should be the result of applying the empty word to a state?
would it be keeping it the same?
Yeah, exactly. I mean, you're not really applying anything, therefore your epsilon is nothing, and so wherever you are, you're going to stay there. So this is Q for all Q in capital Q. I'm not saying that this is complicated, okay? And so the next step then is if the word is not epsilon. So the length of W is greater than or equal to 1. That means W can be written as AV, where A is a letter and V is a word. Okay, now this is sort of belaboring the obvious, but if you have epsilon, obviously you can't split off a letter because it doesn't have one. On the other hand, if the word is not epsilon, then it has to have at least one letter at the beginning. And that's, of course, what we do when we go through this transition with our hot little finger, okay? Because essentially what we're doing is we take a letter and use it up to do that transition, and then we take the next letter and use it up to do that next transition, and so on and so forth. And so that corresponds then to looking at that leading letter of the word, and so we have tau of Q and W, which is of course tau of Q and AV. That's just using that definition. And then we are going to apply that letter A to Q. So this is tau of Q and A. And then to whatever follows, we get a state here, tau of Q and A. And to that then we apply V, the rest of the word, which is, of course, exactly what we're doing very intuitively when we trace a word through that state diagram, because we use up the leading letter, and then to that state where we end up, we apply the remainder of the word. So when we had A, B, B, well, we used up the A, which gets us from Q0 back to Q0, and then we use up the next letter, which is that first B, which gets us from Q0 to Q1, and then we take the third letter, which is B, which gets us from Q1 to Q2, and that's the end of the word, so we end up in Q2. And that is exactly what is being done here. The word has a leading letter, which we call A. Whatever is left is V. And so we use up that letter A, applying it to that state Q where we are. And then for whatever happens here, we get a state, because by definition, this is a state, a single state. And to that state, then we apply what is left of the word, which is V. And that's for all Q in capital Q. Yes?
Professor, could you go through the equation one more time with the letters? I mean, just so I can see it working.
This one?
Yes. So I guess we can grab this, I guess the one that has the 5 B's.
4 B's. Oh, this one. Okay. So you have an A, and then you have a B, and then you have another B, then you have an A, and then you have a B, and another B, and an A, and a B, and so you end up in Q1. Okay? Does that answer your question?
Could we apply the rule to it, or is that just being applied automatically because of intuition?
Oh, you mean this definition here?
Yes.
Well, yeah, you can do that, but of course it's a lot of work. So let's just use a simpler. Let's take BAB. So you have tau of Q0 BAB. That means you have tau of Q0 and B, and the remaining word is AB. And so you look at what is tau of Q1B, and come on, here we go. Tau of Q, I'm sorry, did I say Q1? It should have been Q0. Sorry. Q0. Yeah, I said Q0. I just didn't write it down. So this is Q0. BAB, which is by definition, we've split off the first letter, which is B. So we have that Q0 with that B, which gives us a state, and then the remaining word is AB. So we look up what is tau of Q0 and B. Tau of Q0 and B is Q1. And so we get that. This is then Q1. AB. And by definition, again, where this leading letter is split off, so I have tau of Q1 and A, followed by what is left, which is the B. And so looking up what is Q1 and A, Q1 and A is Q1, so that gives us tau of Q1 and B. And now, by definition, if we slavishly follow the definition, well, we have to split off the leading letter from that, so that's tau of Q1 and B, and what is left is epsilon, because if you have that, it's a single letter in W, then the leading letter, the only one, is split off, and what is left is a V that is epsilon, which is of course permissible. So we have tau of Q1 and B. We look that up. Tau of Q1 and B is Q2. So this is tau of Q2. Oops. Q2 and epsilon, the epsilon being what was left, and now we use the basis element A, and tau of any state under epsilon is that state, so this is then Q2. All right, not quite as long as the 1, 2, 3, 4, 5, 6, 7, 8 letter word, but it should illustrate just as clearly or even clearer how this is working.
Yes, thank you. I didn't realize how long it was going to take.
I know, that's why I didn't let you, I didn't do the 8-letter word. I mean, it is much easier to do that with your hot little finger. So if you go B, A, B, then that's how you end up. This is formally defined, but it really doesn't make it, once you get used to that formalism, it's not really that much more complicated. But it is a lot of writing. Okay, and so now we finally can define what is LFD, the language of all words accepted by the deterministic finite automata. This is simply the set of all W in A star, such that tau of Q sub 0 and W is a final state, an element of F. The language accepted by the deterministic finite automaton D. So this is, of course, where we need the extension of the transition function to words rather than just letters. And that means that now this is a state. Tau of Q0 and W is a state for any word W. And for that state, we can then test, is it a final state or not? Is it in F or not? If it is, the word W is accepted. If it is not, the word W is rejected. Any questions about this?
Hello. In
Yes?
In the past slide where you were doing the transition functions,
Yes.
for the last line, is it tau of Q1 and B equals tau of Q1B of epsilon? Is that still Q1 or is that Q2? In the second tau, is it Q2 or is it still Q1? So like I have it written down as tau of Q1 and B equals tau of Q1 and B and epsilon equals tau of Q2 and epsilon equals Q2.
This
I think
If
it's needed.
Yeah, if I may, I think that the reason why he actually did the epsilon so that at the end you can actually end with just the Q2 and epsilon, leaving it back to the A process. So it would be not necessary but possible to go ahead and put the epsilon in there just so that you can know when to stop.
Okay. So like at the end, I guess we just found out that the final state is Q2. So I think I get it.
We were asking because you couldn't read it.
Yeah, I was just making sure that
It's
that
it's it's Q1. It's Q1.
okay. Thank you.
Yeah.
No, I'm sorry. The complication introduced by the definition is that the basis element is only for epsilon. That's what terminates things. Everything else will still give you taus. The only thing that terminates that sequence of taus is the basis element, basis case, and the basis case is only defined for epsilon. Now, that's why we have to go through that rigmarole of writing B as B concatenated with epsilon, and then splitting that B off, and then get tau of B Q1 and B comma epsilon, and then tau of Q2 and epsilon Q2. You could directly go from that using the definition of tau, which will tell you tau of Q1 under B is Q2. I was just simply slavishly following the definition. Somebody really wanted this carried out, but you can certainly go directly from tau of Q1 and B to Q2 without going through those two intermediate steps. Okay, any other questions?
I have a question.
Sure.
So you were just it was just a thing that when you were doing the equations, you were just going one by one, deleting each letter or getting rid of each letter.
Right. I'm using up basically one letter at a time. Just
Yeah.
like when I go through this automaton, through this graph, I use up one letter at a time. And so the V that I have indicated here is basically whatever is left.
Okay.
So I'm splitting, if I have a word that is of length 1 or more, then I split off that leading letter and I call V whatever is left. And that's basically what I'm doing here. This is just when I go through that graph, well, I use up, say, if I have Z, let's take this again, A, B, B. So I use up the leading letter A, and the V that I have in the definition would be whatever is left, namely BB. And then I have used up the A, so what is left is BB, and then I go and take this one step further. So I use the B, which means the remaining word is V, and then I do that, and so that gets me to Q2.
Okay. For just clarification, when we do this, do we have to say what you did in the third slide? So on B, do we have to write down that we always will split it up?
No, no, this is just the definition. You actually are never going to do that.
Okay.
So don't. It's just that this is the formal way of defining things. And we need that because otherwise we can't really make a cogent argument. Okay?
All right, thanks.
All right, so quickly, what are we going to do for a non-deterministic automaton? Well, it's going to be exactly the same. N is alphabet, set of states, transition function, Q0 and F. So A is the same, Q is the same, Q0 is the same, and F is the same. The only difference is the transition function. And for the transition function, we are going to have a mapping tau that takes a letter, an alphabet, a state and a letter, and maps it into a set of states. So this is the power set of all of states. So this is the set of all subsets of Q. And this is again tau of a state and a letter. So we have tau of Q and A. That is now a set of states P1 through Pm. And little worryingly, M is greater or equal to 0, meaning that there may not be any state in there, which means this is the empty set. So if we look at that transition before, we had Q0, Q1, Q2, and Q3. And now let's assume I'm going to mess with that. I'm going to mess with that diagram. And so I'm going to add another transition under B in addition to the transition from Q0 under B to Q1. I also have the transition from Q0 to Q2. And in addition to that, I am going to delete the transition under A from Q1. So what I'm getting then is I have Q0, it's still Q0, but under B I get Q1 and Q2. Okay, let's look at that. And then under Q1 I get rid of the transition under A and I keep everything else. So there's nothing, and then this is Q2. And from Q2, I have exactly what I had before, Q2 and Q3. And for Q3, I had exactly what I had before. Come on. There we go. So Q3 under A and Q0 under B. So now this is clearly not deterministic because we have two states here and we have no state here. So this is now a situation where the transition function maps a state and a letter into a set of states. Now under Q0 under A we still have a single state, but Q0 under B, for instance, we have two states, Q1 and Q2. Q1 under A we have no state, so that would be the case M is equal to 0. For the other cases we have one single state in all cases. So that means that what we're really dealing with is here another automaton, which can be again written down exactly like before. If I enhance that transition function tau with the indication what is the initial state and what are the final states, then I have that. And now we have to look at two issues. The first one is we want to extend tau to words. That turns out to be a little bit more complicated than before, because if you go from Q0 to B, then you end up with two states. And that doesn't allow us to do the extension that we did before, because that was basically predicated upon the fact that that will always give us a single state. Now it will have to give us more than one state. Okay, this is the set of all sets. It's the power set, and so the set of all subsets. So in this particular case, if Q is 0, 1, 2, I'm doing only 3, then you would have the empty set, you would have 0, you would have 1, you would have 2, you would have 0, 1, you would have 0, 2, you would have 1, 2, and you would have 1, 2, 0, 1, 2. So that's 1, 2, 3, 4, 5, 6, 7, 8, which is, of course, exactly, if you have 3 elements in the set, then the power set of that set will have 2 to the third, which is 8 sets, 8 elements. Does that clarify? You just have to look at what is power set. Okay, so that means we have to extend that to words, but that creates problems. So we'll have to actually extend tau to power set cross A star, giving us power set. And then we have to define L of n. And then, once we have done that, which will take a little bit, we're not going to do that today, then we have to ask a fundamental question. And that
You're muted.
do we gain anything if we let these transition functions be non-deterministic? So obviously any deterministic finite automaton can be viewed as a non-deterministic finite automaton. All right? Because if it turns out that these are all single state sets, then obviously we have the deterministic finite automaton situation. And now we need all that formalism in order to verify that that actually is exactly the same. So if we treat a non-deterministic finite automaton where all these entries are single states, as if we deal with that, then that would technically look like a deterministic finite automaton. If we call that nevertheless a non-deterministic finite automaton, it should be fairly clear that that really is a deterministic finite automaton, which immediately shows that whatever you can do with a deterministic finite automaton, you can also do with a non-deterministic finite automaton. Because all you have to do is pretend that this non-deterministic finite automaton, where every entry is a single state, is a deterministic finite automaton, and that shows you that whatever you can do with the deterministic finite automaton can also be done with the non-deterministic finite automaton. I want to then ask the question, what happens if we have true non-determinism? And in that case, the question is, are there things that can be done with a non-deterministic finite automaton, but they cannot be done with a deterministic finite automaton? And that is something we're going to cover on Monday. Any questions?
I actually do not understand why a deterministic automaton and a non-deterministic automaton can be sampled as the same.
Look, if you look at the definition says you take a state and a letter and you get a set of states. Now, if this M happens to be always 1, don't you have precisely a deterministic finite automaton? I'm sorry, here it is. You have a single state. Well, that would allow you to treat that non-deterministic finite automaton, where these sets are always single state sets. You can obviously treat that as a deterministic finite automaton. Right? Any other questions?
Can you explain why the power set is 2Q?
Well, that's a notation. I mean, in some cases, people write P of Q, which would also be the power set. But basically, it simply says you take all subsets. So the definition is the set of all subsets. Of Q. You can use either one of the definitions, either one of the notations. Doesn't make any difference. But basically, it's the power set. Does that clarify it? Yeah, okay. Any other questions? All right, then I will talk to you on Monday. Have a good afternoon.
Thank you, Professor.
Thank you.
Thank you.
Thank you, Professor.
All right, thank you.
Yeah.